All right, this is Tuesday, February 16th, 2021, lecture presentation on some formulas for basic orbital mechanics. So in particular, I'm going to be trying to guide you through the formulas and equations to deal with calculations involving circular orbits. All right, so in some previous episode, I had presented the formula for calculating centripetal acceleration. And that formula is v squared divided by r, where v is the speed that you're going at any one moment, r is the radius of the circle, and if you're going around the circle at a constant speed, you're actually accelerating towards the center of the circle, and here's a formula for calculating it. If you consider a circle of radius r, and its circumference is 2 pi r, then in a period of time, capital T, you will complete one revolution around the circle, and your speed is the distance that you travel, 2 pi r, divided by capital T, the amount of time it takes you to travel that distance. Well, I can substitute this 2 pi r over T into the centripetal acceleration formula. So centripetal acceleration could be written as v squared divided by r, but it can also be written as 4 pi squared r divided by t squared. This will allow us to calculate the acceleration if we know the radius and period of revolution, or again, given any two of these three variables, we can solve for the other one. You give me acceleration and period, we solve for radius. You give me acceleration and radius, we solve for period. We can solve for speed, given radius and acceleration, and so forth. Okay, then on top of all that, there was Newton's second law, F equals ma. In the case of centripetal acceleration, that means centripetal force is mass times centripetal acceleration, which I can also write as mv squared over r. Great. So armed with that background and skipping doing any examples as a warm-up on how to do this problem, I'm now going to introduce to you a new equation. And this one was developed in the 1600s. So once upon a time, there was an apple tree. Yes. And there was this high school student who got accepted into Cambridge University. But a pandemic broke out and classes were canceled. So he stayed home on the family farm instead of going off to join the freshman class at Cambridge. And while he was on his family farm, they had an apple orchard, and an apple fell from a tree. Now, where I grew up, we also had an apple orchard, and yes, every now and then you could hear a ripe apple hitting the ground. Those were the days. Now, the moon is something you can actually see in the sky if you go outside tonight. If it's clear, you can see a waxing crescent moon in the evening sky, and it rises before sunset. You can see it before sunset. So our young Isaac Newton, while waiting to get into Cambridge, pondered, could it be that the same invisible force of gravity that makes an apple fall to the ground be the force of gravity that makes the moon accelerate in its orbit around the Earth? So he worked out a formula. And to give you some background on his thinking, imagine if I had a candle. So this is one of those candles, candle holder, and here's the candle. That's the flame. Imagine if I could surround this candle with a sphere that has a radius of 1 meter. And on the surface of the sphere, I have all kinds of photodetectors that didn't exist in the 1600s. But collectively, they're going to collect all the energy emitted by that candle. So, consider this. The formula for the volume of a sphere is what students usually remember when I ask them, what can you tell me? And that's 4/3 pi r cubed. But in this situation, we don't care about the volume of the sphere. We care about its surface area. The surface area of a sphere is some different formula. If you're in calculus, you could say it's the derivative of the volume. If you're not in calculus, you would just look it up and it says, oh, it's 4 pi r squared, where r is the radius of the sphere. All right, I just verified it. That is the formula for the area of a sphere. Now imagine if I have a whole bunch of detectors, and each one is, let's say the sphere has a radius of 1 meter, which I don't think even existed back in Isaac Newton's day. I don't think it was invented yet. And that on the entire surface of the sphere, I have a bunch of photodetectors, and each one has an area of 1 square centimeter, let's say. Okay, so I need this many of them to completely capture all the energy coming from this candle. And the candle is shining and it's sending energy in all directions, and I'm collecting it in all directions. And let's say that I measure the total energy is something like 1 joule of energy being emitted every second of time. Okay, great. Now, here's a question. What do you think would happen if I were to remove this sphere and then replace it with one that was twice the radius of the original sphere, and line it with the same size photodetectors, each one 1 square centimeter? Now I'm going to need a whole bunch more of them than before. How many more? Why, look what happens. If the surface area of the sphere that was 1 meter in diameter is 4 pi r squared, then the surface area of the sphere with a 2 meter radius, I'm sorry I said diameter, 2 meter radius is going to be 4 pi open parentheses 2r close parentheses squared. In other words, the surface area of this second sphere is going to be 4 times the surface area of the first sphere. If it's twice the radius, it's going to have 4 times the surface area. Here's a question for you to ponder. What would be the total energy of that candle measured by the second sphere compared to the total energy measured by the first sphere? Okay, so I just paused the video hoping that you would think for a moment, how would the total energy compare measured on the second sphere compared to the inner sphere? The second sphere has twice the radius and therefore 4 times the surface area of the first sphere. It's still just one candle in the center of the sphere. And the candle isn't any brighter than it was for the first sphere, and it's not any dimmer, I should be careful on my wording, than it was for the first sphere. What I'm trying to say is it's still putting out the same total amount of energy that it was putting out before, but now it just travels a greater distance before it's collected. That's the only difference. So it travels twice as far, but I'm still going to collect all of that energy. And all of that energy, the total, should be unchanged. So if it's putting out 1 joule per second of energy, it's still putting out 1 joule per second of energy. The total energy isn't going to change. What does change is the intensity of that light, how much energy there is on each little teeny tiny 1 square centimeter detector. On the larger sphere, there are 4 times as many of these detectors as there was on the first sphere. Yet the total has to add up to the same total energy. So that means each detector on the larger sphere is only getting 1/4 the energy that the same size detector gets on the inner sphere. In other words, the intensity of the light is inversely proportional to the square of the distance from the candle. This is my crude attempt at doing a proportionality symbol for math class. And this is for the intensity of the candlelight. Isaac Newton considered the Earth with that apple being essentially on the surface of the Earth. He knew already that the Earth was a sphere. Remember, Columbus discovered the Americas in 1492. This is already in the 1600s. So yes, by then they knew the radius of the Earth fairly well. He knew the acceleration due to gravity on the surface of the Earth. He knew what the acceleration was of the apple. Galileo had carried out those measurements a generation before he did. So he had this, this is a number. This is a number. Up there in the sky is the moon. Let's say this is the dark side. So here's the moon. Thanks to Copernicus in the 1570s, he knew the distance, the orbital radius of the moon around the Earth. And just by watching how much time it takes the moon to go around the Earth once, he knew the orbital period of the moon was 1 lunar month. So he had enough information that he could predict what would be the centripetal acceleration of the moon in its orbit around the Earth. And he predicted what it would be based on ratioing the intensity of gravity as if it were like the intensity of candlelight. In other words, he developed a formula that said the force of gravitational attraction between any 2 objects in the universe would be some constant. And here's the formula he developed, times the mass of one of these 2 objects times the mass of the other of the 2 objects divided by the distance between them squared. That is from his analogy with candlelight. He reasoned that just like candlelight, the intensity of gravity diminishes as the square of the distance from the source. This is called Newton's Law of Universal Gravitation. And he confirmed it to his satisfaction by predicting what would be the centripetal acceleration of the moon towards the Earth. And I forget the number. It's something like it should be 1/32 of an inch per second acceleration towards the Earth, something like that. And he compared that with the formula and saw that they had the same prediction. So one is based on observing the period of the moon and knowing the radius of the moon and using the formula for centripetal acceleration to calculate the centripetal acceleration. And the other was based on his newly invented formula for calculating gravitational attraction based on his observations of the apple falling on the surface of the Earth. So, ta-da, here is the exciting new equation for us to use. The details are, this is called, they sometimes call it U log, which is short for Universal Law of Gravitation. How about that? Universal Law of Gravitation. The formula is, for any two objects in the universe, the force of gravitational attraction between them is, now technically it's a minus sign, which only tells us it means it is an attractive force. That's all the minus sign means. So I'm probably even going to not bother writing it from now on. But it's there as a physics technicality. Some constant times the mass of first object, mass of the second object, divided by the distance from the center of one to the center of the other squared. So let's list some of those variables. G is called the universal gravitational constant. It is the least well-known constant in all of physics. Its value, as best we can tell, is 6.672 times 10 to the negative 11th power newtons meters squared per kilogram squared. M1 is the mass of the first object. Must be in kilograms. M2 is the mass of the second object, again in kilograms. R is the center of M1 to center of M2 distance, and here's what's really important. It's got to be in units of meters. This is not mass, this is meters. Great. Let's do an example. I have a mass. From my students, I've asked them to generate 3 random numbers. The random mass of the first object is 5 kilograms. The random mass of the second object is 23 kilograms. And the random distance from the center of one object to the center of the second object is 43 meters. Calculate, please, what is the strength of the gravitational attraction between these two masses? A little tip, if you're using a TI type brand graphing calculator, you might want to store the universal gravitational constant in your calculator. You would do that by typing 6.672 second EE, the exchange key, 11, the store button, the alpha key, and G, you should think of some letter to represent the universal gravitational constant. Whatever letter you put in, then press enter. on a TI brand calculator, 6.672, second, EE, exchange key, 11, store, alpha, some appropriate letter, enter, and from now on, whenever you need to use that value in memory, alpha, that letter, will bring it up until you change the value in that memory. All right, calculate please. What is the force of gravity between these two objects? All right, so my students have correctly calculated. I'm going to bother writing the minus sign because this is a physics class where I'm presenting it. So the minus sign means it's attractive. And the numbers that we got is 4.15 times 10 to the negative 12th power newtons. Now it turns out 10 to the negative 12th power is actually one of those Greek prefixes called pico. So I could say this is negative 4.15 pico newtons is the attractive force between these two masses. All masses in the universe attract all other masses in the universe. You are attracted to your parents. Your parents are attracted to you. You're attracted to your classmate. Your classmate's attracted to you. You're attracted to your pen. Your pen is attracted to you. All matter in the universe is attracted to all other matter in the universe, and this formula lets you calculate the strength of it. When you have enough of it concentrated in one spot, like the 10 moles of kilograms that represents the mass of planet Earth, then you get a force of gravitational attraction that, in that special case, is your weight. Okay, so where do I want to go with this? I've presented Newton's law of universal gravitation, and I began by reminding you about the formula for centripetal acceleration. So now we need to put on our thinking caps. Here is the sun, and orbiting the sun is the Earth. And we'll pretend it's a, nice circular orbit and life is good. Now, the Earth doesn't have a string tying it from the Earth to the sun. It's attracted to the sun by Newton's law of universal gravitation. And by Newton's third law, the sun is also attracted to the Earth. Yep. Okay. Now, riddle me this, Batman. The Earth is in a circular orbit around the sun. So we can calculate the centripetal force needed to keep the Earth in its orbit around the sun. That would be equal to the mass of the Earth times the speed of the Earth squared divided by the orbital radius, which is the distance from the center of the sun to the center of the Earth. That is the formula for the Earth's centripetal acceleration. Separately, I just developed for you Newton's law of universal gravitation. And I'm going to leave off the minus sign because I'm getting lazy, I guess. And it said it's equal to this constant times the mass of the sun times the mass of the Earth divided by the distance, the orbital radius from the sun to the Earth squared. These are two separate formulas. Centripetal force, Newton's law of universal gravitation. Which one is the stronger of the two? Ponder that one. All right, so consider this. What will happen to the Earth if it turns out that the force of gravity, the sun pulling on the Earth, is greater than the centripetal force needed to keep the Earth in its orbit. If it turned out that the force of gravity of the sun pulling on the Earth were greater than the centripetal force needed to keep the Earth in its orbit around the sun would pull the Earth towards the sun. We would all burn up and die. Speculate, please. What do you think would happen to the Earth if the force of gravity of the sun pulling on the Earth were less than the centripetal force needed to keep the Earth in its orbit around the sun? Okay, so if the force of gravity were less than what's needed to keep the Earth in its orbit around the sun, the Earth would essentially spiral farther and farther away from the sun. It wouldn't go flying off on a tangent unless the sun were completely shut off. And we're not doing that in this situation. We're just saying, oh, it's not strong enough to keep the Earth in this orbit around the sun. So then the Earth would go away. Well, for 5 billion years, we haven't burned up and died, and we haven't frozen to death and died. Although people in Texas are maybe scratching their heads today, and we have a refugee from Canada, maybe because it's happening. Yikes. But no, for 5 billion years, the Earth has orbited the sun. So from that, we can conclude that we can safely set these two equations equal to each other. Centripetal force, mv squared divided by r, can be set equal to g m1 m2 over r squared. One of the r's will cancel. One of the two masses will cancel, and the one that cancels is the mass of the object in orbit around the central body. So when we start using the software called STK, they generically call this the central body. In the case of the Earth orbiting the sun is the central body. In the case of the moon orbiting the Earth is the central body. In the case of a satellite orbiting the moon is the central body. In the case of the sun orbiting our galaxy, the galaxy is the central body, and so forth. So that's the one that cancels. I'm sorry, that's the one that does not cancel. Okay, so cancels the object in orbit. It's the mass of the central body that is left. So here's the exciting equation. It says v squared equals universal gravitational constant times the mass of the central body divided by the orbital radius. Mass of central body, of course, in units of kilograms. Orbital radius, and here's the kicker. Please do this always in units of meters. Again, that's not kilograms, that's meters, children. And therefore, the velocity will work out in units of meters per second when we get done with this. Meters per second. Let's do a fine example with the Earth. And an object orbiting the Earth at a radius of a random selected value of 90 90,000 kilometers, which puts it about a third of the distance to the Earth's moon. And we'll treat it as if it's 3 sig figs, although it's written to just 1. And calculate, please, what will be the velocity of a satellite orbiting the Earth at an orbital radius of 90,000 kilometers. Of course, you'll need to use the mass of the Earth in this calculation. And I'm going to tell you it's a value of 5.974 times 10 to the 24th power kilograms. If we were to add in the mass of the moon, this would be fairly close to 10 moles of kilograms. It'd be something like 6.03. All right. Calculate, please, what is the speed of this satellite allegedly orbiting the Earth at an orbital radius of 90,000 kilometers? Okay, so in this example, the formula is the square root of gm over r. So you're going to be taking the square root of 6.672 times 10 to the negative 11th newtons meters squared per kilogram squared times the mass of the Earth, 5.974 times 10 to the 24th power kilograms, divided by the orbital radius. But careful, I presented it in units of kilometers, but it has to be calculated in units of meters, knowing that 1 kilometer is 1,000 meters. I would submit that 90,000 kilometers is 90 million meters. All right, calculate, please. Beep, beep, beep. Okay, ta-da. The answer is 2,100 meters per second. That's to 2 sig figs. To 4 sig figs, it was 2,104. And so to 3 sig figs, we would say it's 2.10 kilometers per second. Okay, to 3 sig figs, 2.10 kilometers per second. Okay, now I have a little geometry factoid I want to share with you as well.
Wait, Mr. Turek, I have a question.
Okay, so as a reminder, this formula that I've developed and thrown at you is the one used to calculate the speed at which an object is undergoing uniform circular motion. So at the moment, I'm only dealing with circular orbits. And what I've tried to get us to so far is one formula, this one, for calculating the speed of whatever satellite is orbiting some central body. So the Earth is a satellite of the Sun, the Moon is a satellite of the Earth, and so forth. So this formula is for calculating the speed at which we are gravitationally orbiting some central body. And for now, we're only dealing with circular orbits. Later, I want to teach you how to deal with elliptical orbits. So now I want to give you a little bit of geometry that says, look, if I know the radius of my central body, usually we write that with capital R. That's different from the orbital radius, which we usually write with lowercase letter r. So capital R is radius of central body. And that can be in meters, it can be in kilometers, right? R is called the orbital radius. And that's the size of the orbit. very different. These are two different radiuses, but they're both radii, right? Two different radii, but they're both radii. So one little geometry factoid is that if I am in an orbit of radius r above a central body of radius capital R, then we could say that this distance here is called the altitude h, and that's measured above the surface. So just be aware that I want to be able to give you problems and say, I'm at an altitude of 5,000 kilometers above the surface of the moon. Calculate, please, dot, dot, dot. So when I give you the altitude, you would add to that the radius of whatever the central body is, and these two added together will be equal to the orbital radius that you would use in the formula. So in this example that we just did, the orbit radius r was 90,000 kilometers. The radius of the Earth is 6,378 kilometers. So if I subtract 9 minus 1 is 2, 9, 8 is 6, 9 minus 6 is 3, I get apparently 83,620 kilometers is the altitude of this satellite above the surface of the Earth. And here we're treating the Earth as a perfect sphere. We're using the average radius of the Earth, dot, dot, dot. Okay, I need to move on because there's more I want to cover before this period ends. I had said earlier that v, the speed at which you're moving in a circular orbit, could be represented as the circumference of the circle divided by the period of time it takes for you to go around the circle once, capital T. But we also just looked at this formula that said v squared is equal to universal gravitational constant times the mass of the central body divided by the orbital radius. So now, for my next magic trick, I'm going to take this expression for orbital speed and substitute it there in that formula. Well, that means I'm going to have to square everything here. So 4 pi squared r squared divided by t squared is equal to g times m divided by r. Now, for reasons that are kind of humorous to me, my students tend to want to cancel the r's. They do not cancel. No. I can eliminate the one on the right by multiplying both sides by r. But that makes it r cubed on the left. Yes, 4 pi squared r cubed over t squared is equal to g times m. Next, I'm going to multiply both sides by t squared. So now I have 4 pi squared r cubed equals gmt squared. Next, I'm going to divide both sides by gm. So at last, I have t squared equals 4 pi squared r cubed divided by g divided by m. This is the other big formula that we're going to be using these days. It's called Newton's version of Kepler's third law. T squared equals 4 pi squared r cubed divided by g divided by m, where t is the orbital period. And here's what's important. It must be in units of seconds in your calculations. R is the orbital radius, and it must be in units of meters in your calculations. And m is the central body mass in units of kilograms. As with all physics equations, if I give you all but one of these variables, you rearrange that equation and solve for that one unknown. So let's do some sort of random example. All right, so we're going to make up a random example. And for this example, we're going to use the mass of the Earth per student request, which I remind you is 5.974 times 10 to the 24th power kilograms. We will use it multiple times. If you want, you now know how to store numbers in your calculator memory, but it's a big universe, right? So are you going to store the mass of Pluto, the sun, all the planets, all the stars? I don't think so, right? But the Earth we use from time to time. Now, we can either consider the period of time or the orbital radius and solve for the other. I propose that this time, heck, we'll just continue with the same example as before. So the orbital radius, we decided in the previous problem, was 90,000 kilometers. And of course, you should be thinking, hey, those aren't meters. That's actually 90 million meters. Calculate, please, what is the orbital period of a satellite that is at an orbit radius of 90,000 kilometers from the center of the Earth. Okay, calculate the orbital period in units of seconds. So you're going to be taking the square root of 4. So if you want, yes, you can pull that out and say 2. The square root of pi squared. So you can also pull that one out of the radical sign and say it's 2 pi. But underneath the radical sign, you can't avoid this. It's going to have to be r cubed, where r is in meters, cubed, divided by g, divided by the mass of the Earth. And by the way, there's the astronomical symbol for the Earth. Astrological symbol, maybe as well. All right, calculate, please. Okay, well, for my convenience, I actually wrote a program to do this sort of calculation for me because I did this over and over and over again as I did my research. So here you can see the result of my program. For the Earth as a central body, a radius of 90,000 kilometers corresponds to an altitude of 83,622 kilometers. The period to complete a circular orbit is 268,709 seconds. Too many sig figs, but I always like displaying it to the nearest whole second. And then, what is that converted? Oh, man. We missed it, right? So it converted it for you into minutes and into seconds. I'm sorry, minutes and hours. And just to see it before it fades, that said it was 4,478 minutes, which works out to a little over 3 days. 3 days would be 72 hours. So there you go. And we've already calculated the velocity was 2104 meters per second. So this is a program I wrote because I do this a lot and I love doing this. You can study how to write programs and then build one yourself. But don't just download one. Build one if you're going to do this at all. Okay, we have time for perhaps one final example. And let's choose again the mass of the Earth. And this time an altitude above the surface of the Earth. Okay, per random student, multiple guess, 15,000 kilometers above the surface of the Earth. Even before we do new calculations, because it's closer to the Earth, it's going to go around faster and faster. The period is going to be less than the 3 days that it was before. The speed is going to be greater than the 2 kilometers per second that it was at 90,000 kilometers. Okay, so calculate, please, everything. What will be the speed in its orbit around the Earth? What is the period of time it takes to orbit the Earth? And what is its orbital radius? Now, as you work out these three answers, really, you should do the orbit radius calculation first and say, oh, that's equal to the radius of the Earth plus its altitude. After you have this answer, then you can do either the velocity or the period, because these are independent. Velocity is the square root of gm over r, and the period is is 2 pi times the square root of r cubed over gm. Now you can start to see why I would write a program to do this for me. All right, calculate please everything for a satellite at an altitude of 15,000 kilometers above the surface of the Earth. Okay, just to show off the program I wrote, I set it up so that, first of all, I can choose what kind of central body I'm talking about. These four are the ones I commonly use in my course: the Earth, the Moon, the Mars, and the Sun. If I want to put in some completely new central body, then this choice would ask me, what is its mass? What is its radius? In this problem, I'm choosing the Earth. Okay, next, what kind of orbit am I talking about? We're starting off with circular orbits, so choice 2 on my menu. Next, what is the information that is given about the circular orbit? Is it the radius, the altitude, or the period? In this example, it was the altitude. And finally, I now enter the altitude above the surface of the Earth, 15,000. Notice that I work in units of kilometers when I run my own program. Enter. Here's all the information. Here are the answers. The altitude is 15,000 kilometers. The radius is 21,378 kilometers. The period of time, 31,108 seconds, which corresponds to a little over 8.5 hours. And the orbital speed is 43.18 meters per second. I'll do, I guess, one last example. I'll just make one up. All right, per student request, this final example is at an altitude of 25,000 kilometers. I suggest you pause this video and work out the answer yourself and resume it. Here's the answer. A satellite orbiting the Earth at an altitude of 25,000 kilometers above the surface would have an orbital radius of 31,378 kilometers, a period of a little over 15 hours, which is 55,317 seconds, and an orbital speed of 3,564 meters per second. more than half a mile. Oh, what is that? More than 2 miles per second orbiting the Earth. All right, so let's quit and say this concludes my educational program for today.